we introduced some important notions, and now we'll introduce two key tools that we will be using repeatedly, and one of them actually all the time. And we start with a simple question. How much is square root of 1.25? And it's a very good question, because there is no direct procedure for calculating this number, unfortunately. So we will have to approximate it somehow. And this brings me to this tool I was talking about. I can see this as a problem of actually knowing something or learning something about a function square root of x. There are some points that we know quite well. For instance, point 1, definitely a good one. And point 4, that's the next one that we know quite well. But unfortunately, our point 1.25 is somewhere here, where we do not know the square root well. Well, there is a very handy tool, which is called Taylor expansion or Taylor polynomial. Actually, there are two forms. Here is one, which is fairly popular in calculus classes. Fx can be expanded as fa plus f prime a x minus a, and so on. I'm pretty sure that you know it. The other form works with f a plus h. And it's very similar. In fact, it's just a substitution. So this is trivial. However, the practical application is much different. Let me add another one. Of course, in the best scenario, you would know both of them and use them accordingly and confidently. But if I had to choose one for numerical analysis, it would be the second one. Typical scenario. I know situation at some a quite well. I'm happy there. This is my a. I am happy here. Instead, I'm supposed to move someplace else and see what's happening there. And experience tells me that the farther I go from this nice place, the trickier the things will be there. So it would be nice to have a measure of distance, how far I am from this nice place. And that's exactly the h here. So this is a natural way. I know how far I am moving away, and I get some reaction from the system or from whatever I'm looking for. So that's my setup. Let's play with it. Let's apply it to square root of 1 plus h. So my function is square root of x, which is x to 1/2. Okay, the boring part. The derivative is 1/2 x to negative 1/2. The second derivative is negative 1/4 x to negative 3/2. And the third derivative is 3/8 x to negative 5/2. The fourth derivative is minus 15/16 x to negative 7. Do I really need it? I don't think so. Anyway, here we go. We need to figure out how much it is when I substitute my center a in it. So I'm interested in f at 1, which is 1. That's easy. And let's play here. If I'm putting 1 for x, then these square roots are going to be just 1, because this is some power and a square root. These are all just 1. And I actually see the coefficients here. 1/2, negative 1/4, 3/8, minus 15/16. Something like that, okay? So that's the coefficients I will be using here. 1/2 h minus 1/2 times 1/4 h squared plus 1/3 factorial is 6, 3/8 h cubed minus, okay, 4 factorial is 24 times 15/16 h to the power 4 plus, and so on. That's how the polynomial looks like. Do I like it? That's a good question. Okay, let's see. One more line. 1 plus half h minus 1/8 h squared plus 1/16 h cubed Isn't that nice? Minus. Okay, 3 cancels, and I get 5 on the top, and I can do nothing about it. And this is multiplied by 8, and I get 128. Okay, I don't like it as much as I did before. Okay, hopefully I did make a mistake. If I did, doesn't really matter. Okay, let's see, what do I do with this? Well, that's an infinite polynomial, and I don't have time for that. So I'm going to pick a piece of it. Okay, how about square root 1 plus h could be something like 1 plus 1/2 h. Or perhaps square root 1 plus h could be something like 1 plus 1/2 h minus 1 over 8 h squared. Sounds good. I can create many approximations like that. By the way, when I'm writing 2 wavy lines, this is like equality which is drunk. Fuzzy equality. So I'm saying it's sort of equal, but I don't know exactly how close. So I'm using this when I'm just trying to make some idea. When I'm just shooting blinds. In a way, it's educated guess, but it's not too educated. I'm not claiming any mathematical statement here. This is just intuitive reasoning. Okay? So that's my thinking. I think that this should be true. Okay, I'm interested in 1.25, so I can take h being 0.25. h is 0.25, which is 1/4. Let me put it here somewhere. So the square root of 1.25, according to the first formula, will be 1 plus 1/2 times 1 over 4, which is 1 plus 1 over 8, and this is some number. Actually, this is not equal. This is wavy line. So this is like 1.125, I think, something like that. Or I can try to use the second formula. 1.25 is about 1 plus 1 over 8, let's cut it short, minus 1 over 8 times 16. Wow, that's a huge number. That's some number. If I had a calculator on me, I could calculate it, but I don't really care. So as you can see, I can use the Taylor polynomial to obtain approximations, but the key question is now, how good are they? Because if you remember numerical methods, what does it mean? Well, that's a numerical method for approximating square root. And I'm interested in the error of the method. It depends on h, obviously. The farther I go from a, the larger the error. That's to be expected. What is the error? By definition, error is the actual value minus the approximate value. So I look at this equality, that's the actual value, and I want to subtract the approximate value. Well, I can see the outcome here. That's the error. The tail, that's the error. Or that's the error, depending which approximation I'm choosing. So for the first one, you could call it a linear approximation. Linear approximation of the square root on the neighborhood of 1. There the error is minus 1 over 8 h squared plus 1 over 16 h cubed minus, and I put 3 dots. I don't like that fraction that much. For this, that's a quadratic approximation. Quadratic approximation of root on a neighborhood of 1. Sounds good. Here the error is 1 over 16 h cubed minus, okay, I will have to write it so that there is at least something here. And now a natural question is, which one of these two is better? Now, intuitively, I would say that this one is better, this one, because it uses more information to get my estimate. How can I tell? By looking at these errors. And there I need to know something about h's, about power of h's. Let me do some, let's say, intuitive justification for what I'm going to do. Let me remind you of something that you know from calculus class. When you are comparing powers at infinity, then you know that the highest power always wins. It prevails. And you can even put some really huge constant in front of the smaller power, and it doesn't change the outcome. when you look for the value of this expression when x is large, you can just put it into cube and you get very good approximation. And the closer you go to infinity, the better the quality of approximation. This term becomes negligible compared to x cubed. Now, this thing, it has a specific meaning. When I say f is asymptotically equal to g at a, it's the same as saying that limit x going to a fx over gx is 1. Now, there are several definitions. You can also ask for some positive number here, but it's better with 1. Okay? So that's how I'm using it. Okay, this only works well for non-zero functions, for functions which are not zero at a. This tells me two things. First of all, it tells me that they have the same value around a, but it also tells me that they go to this value at the same rate, because this compares the rates of those two functions. So when I draw graphs, they actually merge around a. So that's what I want to see, for instance, when I'm doing the Taylor polynomial. And if you remember, this is a quadratic Taylor polynomial which I'm attaching here. So I'm attaching here a quadratic polynomial. And when you look here, you can see that the values agree, but also the tendencies, the increase, decrease, the shapes agree. And that's exactly what I would like to see here. I could write just one wavy line and say that this is asymptotically equal. And I can prove it. And once I prove it, I can actually write it. That's the beauty of it. Now, this brings me back here. This is how it works at infinity. The highest powers, they definitely win. They totally overwhelm smaller powers. And again, you can tell by putting them into a ratio. When you put x cubed and divide it by x squared, the outcome at infinity is infinity, because this one is infinitely larger than this one. Okay? The same thing is happening with h's, or x's if you want, around 0, but it's exactly the other way around. So, around 0, when two powers meet, the lower one wins, no matter what you put with the higher one. And again, they win overwhelmingly, because when you put limit h going to 0, h squared over h cubed, let me put it to 0 from the right to avoid troubles. This is just a limit, h going to 0 from the right of 1 over h, which is infinity. This tells me that when I'm near 0, then h squared is infinitely larger than h cubed. Here is a picture. This is h. This is h squared. Now at infinity, h squared dominates h. But when you go to 0, it's exactly the other way around. And you can see here that the ratio between them is really huge, because h is still going slowly to 0, but h squared is already there. So the lower power, which is h, is almost infinitely times here, but here actually in limit infinitely times larger than the higher power. It's the reversal of the usual roles. Which means that when they meet, then the one which is smaller, which is the higher power now, can be ignored safely. What does it mean? It means that here I can ignore the higher powers around 0, and only the highest one wins. This is approximately minus 1 over 8 h squared. Here I have lots of power. Why did I write 5 here? Of course it's 4. 4, 4, 4. Yeah. Sorry about it. Lots of powers. And we now know that around 0, the smallest one will be the most dominant, will be the largest of them. Okay? So I look at all the powers and I ask, which one of them is dominant? The answer is the smallest one, which is this one. Which tells me that the error for the second attempt for the quadratic approximation is asymptotically 1 over 16 h cubed. So knowing how the powers behave around 0 allows me to look at an expression and simplify it, capture the essence of it, capture the dominant part. So this is the error for linear approximation, and this is the error for quadratic approximation. I captured its essence in one simple expression, and now I can compare them. Now remember, lower power is dominant. It's larger, around 0. It's the other way around. So this one is larger, this one is smaller, in fact, infinitely many times larger than this one. But I want a small error, so this one is better. This one is more precise when I go to 0 with h. And now my intuitive feeling that this one should be better is confirmed mathematically. Because this is a higher power, it disappears faster. Now, how do I see it in this picture? Well, h cubed looks somehow like that. And it would seem that over here h squared and h cubed are sort of like similar, very different from h. But the fact is, if you focus here, if you take a magnifying glass, you will see that if you blow up the picture a little bit, that in fact h squared compared to h cubed also does something like that. This is h squared and this is h cubed. So again, when you compare them, just these two, there is this dominance effect that h squared is much, much larger, infinity times larger, which you can compare by looking at the limit. So the second formula is much better. Does it work in applications? The answer is yes, or in practice. Let's make an experiment. Here is my maple. No, here's my maple. What you see here is a plot. What am I plotting? I'm comparing square root of 1 plus h, which is this one, and I subtract 1 plus h over 2, which is my approximation. This is a straight line which approximates, okay, I put a straight line here, a tangent line. So you can also say that I try to approximate the square root using the tangent line. Now, from my analysis, it seems that the error should be minus 1 over 8 h squared. And that's exactly what I hope to see here. Yes, minus 1 over 8 h squared. Now, there are two colors. The actual error is in red. That's the difference. And my estimate, which I obtained by the analysis, is in the navy, which is like a blue. Let's fire it up. Bang. Okay, let's make it larger. Let's have a look at it. Now, that's an interesting curve. They look similar, which is nice, but they also look different on the right. Now, notice that h, which is the horizontal direction, is 1 and 0 here. So this actually refers to the range between 1 and 2. I'm looking at the range between 1 and 2, and I'm comparing approximations by tangent line and by square root, and the square root. So obviously, around 2, there will be a difference. So the error is quite large. But also, when I'm around h is equal to 1, how did I get my estimate? I got it by ignoring higher powers in the tail expansion. This is the exact formula for the error, and I ignored the tail, and I just took the dominant term. But when h is equal to 1, this is not a small number. And this is not a small number, and so on. Well, they are small, but they are not too small. So the difference between the red and the blue curve is exactly the part which I ignored. And it's quite large on the right. But when h is getting small, then the two curves are getting closer and closer together, because for small h's, they really are almost the same. Now, what I'm going to do, I'm going to change the range. Instead of going between 0 and 1, I will go between 0 and 0.1, which means that I will essentially focus just on 1/10 of the graph, on this little part there, and see what happens. And you can see that the error is still quite large here, relatively, but the two curves already got much closer. So they really are very good approximation. I mean, this simplified version is really almost the same as the actual error. And you can see nicely, okay, let me try one more, 0.01. And now they are almost the same. You can see that the error is still quite large, but it doesn't matter whether I use the actual error, which is here, or the simplified version. This really is a good expression or good description of the error when h is really small. Very, very nice. Okay, let's try with the second one. I'm going back to my original game. Now I will subtract 1 plus h over 2 minus h squared over 8. So I'm subtracting the quadratic approximation, and now I strongly suspect that the error is h cubed over 16. That's my suspicion. Bang. Okay, now the error is positive. Yeah, makes sense, it works. And again, on the right, when h is really large, I'm actually ignoring quite important chunks of the error, so the two curves are not very close, but they seem to be going along the same direction, sort of, or the same behavior. So let's focus right away, and this is much better. Now the range is between 0 and 0.1, and you can see that the two curves, the actual error in red, and the approximation of it in blue are really close. And still one more, 0.01. Wow, that's a nice match. Yeah, I can see two curves. When you look there, you can see some red pixels on the right towards the end. So this is a very good match between an infinite polynomial, in fact, and 1 power, h cubed over 16. So this shows that, at least for this particular example, this all makes sense. So first of all, Taylor expansion, a very useful tool. And then when you are dealing with errors, we can ignore terms which are not really important. We usually have h small because we don't want to stray too far. That's dangerous in numerical analysis. So when h is small, it makes sense to drop terms which are negligible. And for that, we are using the scale of powers. Now, this is one possible way to express the error. I can say that the error is asymptotically minus 1 over 8 h squared in the first case, and the error is asymptotically 1 over 16 h cubed in the second case. This has the advantage of precision, and sometimes you need it, and then it's nice to have it. This, by the way, calls for an interesting comparison. What I'm going to do now, I'm going to compare the two errors. The actual errors, not their estimates, but the actual errors. And I will compare them again on the range 0, 1. Now the blue one, it's the one which I think that it's better, the quadratic approximation. And you can see it here. The red curve, that's the linear approximation by tangent line, and the error seems larger. And they seem to both go to 0. So on the first side, there is not much difference. But you can notice that the cubic error hugs the x-axis or the h-axis much closer. Let's see what happens if I focus closer to the origin. Now you are starting to see the difference between two different rates of convergence. You can see that the blue curve is hugging the h-axis much closer than the red one. And if I move even closer to the origin, if I put my magnifying glass there, I will get this. Now the blue curve is almost equal to 0 everywhere, while the red curve is still slowly, relatively, trying to get to 0. So that's the actual difference between h cubed, which is hugging the h-axis over here, while the h square curve is still going there. It looks almost like a straight line, but it's not true. But there is a big difference between the rate of approachment. Okay. That's enough maple for today. And let's go back here. There are two possible ways to look at this. Sometimes you need a very good information about the error, and then you really use this asymptotic equality. And that's the way to go about it. However, sometimes you don't really care about precise information, you just care about trends. I don't really care about 1 over 8, or the minus here, or 1 over 16. When I'm choosing between these two methods, which one of them is more preferable, I simply look at h squared, h cubed, and I can see the difference. I don't need to see the constants. It would be nice to have a mathematical notion which allows me to look at an expression like that and just capture the essence, but the basic essence, not some details like constants. The basic essence, which is h squared here and h cubed here. And there is a notion like that. It's a notion called capital O. Let's have a look at it. Okay, now we have two functions which are defined on neighborhood of some center A. Now what is A in this picture? Well, it corresponds to this situation. So here, the center of our attention is 0. We are interested in what happens when h goes to 0. So 0 is a in this definition. We have two functions around 0 in our case, or some a, and we say that the f is capital OG. Okay, let's go to the end. If there is an inequality. So f is the function which I have in this definition, and g is the function which I want to use for capturing the spirit of the function. So what I'm claiming here that EH is capital O H square. H square is the essence of this long formula. And I dropped the constant because I don't care about it. So that would be the notation that I want to introduce here. What does it mean? It means that I can use this function g, which is over here, as an upper bound for the function f with some constant. Now notice that this constant c is arbitrary, and I don't need this everywhere, I just need it on some neighborhood. So what does it mean? Well, let's make some room. Okay, here we go. By the definition, when I write something like this, it means that the actual error, which we can see over here, minus 1 over 8 h squared plus 1 over 16 h cubed minus and so on can be estimated by some constant times h squared. That's what it says. So I actually have a control over how fast this grows, or rather disappears to 0 in my case. And this is true on some neighborhood for h small. How small, I would have to specify it. If I want to prove it mathematically, I have to do some work. This is not trivial, but it can be done. Typically, you look for a neighborhood where h is less than 1, let's say less than 1/2. Then you've got a nice geometric sequence going, and you show that this is all small. You just need to make these coefficients somehow bounded. And then it can be done. It's not difficult. So mathematically, one can prove an inequality like that on some neighborhood of 0 for h, and then we can say that this is true. But for engineering calculations, we usually pick up the smallest power, and in 9 cases out of 10, this will be okay, this will work. Similarly, for the second approximation, I can write that EH is capital O H cubed. And that's exactly the information I want to see when I'm choosing which method is better for me. This one is better because it has a higher power here. Notice how it goes about. First, I determine a precise form of my error. And when I want to shorten it, let's say into the capital O notation, or big O, I'm choosing the lower power because that's the biggest. So I have to choose the lower power here. And I get that EH is big O H squared, and so on. But then when I'm choosing methods, I'm not choosing the lower power, but the higher one, because this one is larger, so I don't want it. Okay, so there is a reversal of my thinking. Okay, this capital O notation is very useful. Intuitively, I see it as a container. This is a container which contains all the possible polynomials which have H squared as the dominant term around 0. I should add properly where it is done, at 0. Because at infinity, it's another way. It's the other way around, so one has to be careful. So this is always, in numerical analysis, automatically, it's at 0. Okay? This is a container for all polynomials. So I can, for instance, look at this expression, which we have over here, and I can express it like that. Square root 1 plus h is 1 plus 1/2 h plus OH squared. And people who are experienced in numerical analysis, and you will be soon too, just look at it and they can see that they have approximation. And then there is some error term which is dominated by H squared. So you get perfect information all in one package. And now this is a proper mathematical equality. This is appropriate notation. So this capital O is actually allowing you to do imprecise calculations in a precise way, which sounds like a contradiction, but it's not. Because I can now deal with this formula in normal way. I can apply algebra to it, play with it, and there are some rules which will allow me to do it. And we will look at those rules in a second, but just for completeness, let me put here another formula. So that's another formula. Now, I can ask, find an approximating formula for this function with error h cubed, and that would be the answer. Or I can ask, find approximating formula with error h squared, that would be the answer. So that's another way to get here. I can ask questions. I can ask for linear approximation, I can ask for approximation by tangent line, or I can ask for approximation with error h squared, and it's all the same. Okay? So it's very convenient. Let's have a look at some rules. The first rule tells us what happens when two different powers meet. Now, remember that lower power means that it's dominant, that it's large. So b is larger now, b is larger, so h to b around 0 is something small, smaller than h to a. So when a smaller meets the larger one wins. So the power h to b gets swallowed up by capital O h a. Just like here, h to power 4 got swallowed up by lower powers in O, big O notation. Okay? Or you can see it here. We have the error estimate, and the lower power 1 and the higher powers that were swallowed up, they are included here. And the last slide for today. Here is what happens when two O expressions meet and they are added up, or you make a linear combination. You can also multiply them by some numbers. Now, we noticed before, we commented on it, that when you put some coefficient in front of h, or h squared, whatever, the big O notation doesn't care because it also has constant here. So this constant can take off all the coefficients here. No problem there. So when you have expressions, capital O something, and you multiply them by numbers, it doesn't really change anything. And now when two of them meet, the one which has more dominant power wins. But around 0, the more dominant power is which one? The smaller one. A is smaller than B, as you can see here. So when two O's meet, in addition or subtraction, the more dominant one, the lower power, it actually wins. Now, this is easy when you imagine that this capital OHA, that's actually a container for polynomials. So you can see polynomials meeting, and they are added. You add polynomials. Who wins? Well, the one with dominant power. So for instance, these two polynomials, if I add them, this one wins because it has dominant power. All these other powers are negligible compared to h squared. Okay? What happens when two O expressions get multiplied? Well, again, that's simple. I imagine two polynomials. I multiply them so all the powers are added up in different ways. Well, let's have a look at an example. Let's say that O h squared meets, by multiplication, O h4. Well, how do I imagine it? This is some polynomial which has h squared as a dominant power. So it's some constant times h squared plus another constant h cubed plus another constant h to the power 4 and so on. And this gets multiplied by a polynomial which has some constant times h to 4 plus another constant times h to 5 and so on. And now those polynomials get multiplied out. How do you multiply out polynomials? Everybody goes with everybody. Sounds good. Anyway, they all get multiplied out. And you get a huge polynomial. There will be all kinds of powers. And these polynomials can be finite or infinite. I don't know and I don't care. Okay? Now there are lots of powers. And the question is, which one of them is dominant? The answer is the smallest is dominant. Where do you get the smallest power? You get the smallest power here, you get the smallest power here, and multiply them. So what do you get? H squared times h to the power 4 is h to the power 6. And that's it. That's exactly the rule that we can see as the second one. OH to A, OH to B is OH A plus B. That's it. I'm adding the dominant powers. Okay? Okay, the last rule. What happens if you take OH to something and you multiply or divide by some factor of h? Now, this is sort of like a companion to the second part. In the second part, we multiply. In the third part, we divide. But the problem is, dividing O expressions is not so easy. There can be some troublesome points. So I'm just dividing by h to some power. Well, this is also very simple. You have some O, let's say h squared, which is a polynomial with h squared as the dominant power. Dominant means the smallest one. So you take such a polynomial and you divide everything by h to a. So you decrease all the powers by a, by the same amount. And then you ask, who is dominant? This is very simple. When you are using it in applications or some calculations, this all comes natural. So, so far it's just a theory, and already in the next lecture we'll be using this heavily. So hopefully you will get familiar with it. If there is something which is not quite clear to you, think about it a little bit. But that's it for today's lecture. See you next time.